Hello, I welcome you all. The problem reads, the drinking fountain is designed such that the nozzle is located from the edge of the basin as shown. Determine the maximum and minimum speed at which water can be ejected from the nozzle so that it does not splash over the sides of the basin at B and C. This problem is coming from the Engineering Mechanics Dynamics 14th edition by R.C. Hibbeler. Right, just a quick reminder of the basic equations. We have velocity, which is time derivative of position. We have acceleration, which is the time derivative of velocity. And we have one derived equation from the two. And then from these three kinematic basic equations, we can derive quite a couple, depending on the boundary conditions. Of course, the basic one that we usually use is when acceleration is constant and t is equal to 0. Then we have additional boundary condition S naught and V naught. And from this, we can have the following equation: S is equal to S naught, V naught t plus half AC t squared. We have V equal to V naught plus ACT. Then finally we have V squared equal to V naught squared plus 2AC S minus S naught. Right, so from this particular question, we are going to have two components from this velocity. Initial velocity will have the vertical one and the horizontal one. And let's label them. So this we're going to call it Vx, which is constant throughout, and by this we mean acceleration is going to be equal to 0. So this is going to be equal to Va cosine 40. Okay. Then this one is just going to be equal to Vay equal to Va cos 40. All right. Cos 40. All right, there we go. So with this information, what we need to do now is to find, for me, I'll find the time it takes from A to B and the time it takes from A to C. Use that time to compute. In fact, from A to B, I'm going to find the time, and then with that time, I'm going to compute VA. I'll do the same also from A to C, find the time, and that time used to compute VA, because there are going to be two VAs. So there will be VA velocity that we need at B, which will be the minimum, and velocity that we need at C, which will be the maximum. Right, great. So let's start the work. So I'll say from A to B. All right, from A to B, and in this particular part we are just looking for so say V, we are looking for V minimum. Okay, let me just leave it like this. So let's start with horizontal motion. And of course we'll go with this equation. Okay, horizontal motion. So what we need to do now, let's check, is this one a good one? Yeah, I think it is. So we have S equal to S naught plus Vt plus half AC t squared. Of course, our S in this particular case is just going to be equal to, I knew this is our reference. Our reference is here. Okay, so that's our reference. Our reference is at this point here. Okay, this is our reference. Great. So S is just going to be equal to horizontal. We are from A to B is 0.1 meters. S node is equal to 0. V node is equal to VAX, which is just equal to VA sine 40. Of course, AC is just equal to 0. So from this we have 0.1 equal to VA sine 40 times T. Okay, so I can make VA in advanced subject to formula. It's going to be equal to 0.1 divided by T sine 40. Okay, so then let's go to vertical motion. We go to vertical motion. Vertical motion, we are using the same equation. So S is equal to S naught plus V naught T plus half AC T squared. Our S is just going to be equal to 0. Our S naught is 0.05, which is 50 millimeters. Converting everything to meters, I mean 50 millimeters to meters is 0.05. And then we have V naught, which is equal to VAY and is equal to VA cos 14. And then we have AC, which is equal to minus 9.81. Right, so writing this, we're going to have a 0 is equal to 0.05 plus VA cos 14 decrease by T, then minus half 9.81 by T squared. Okay, so what we need to do now is we're going to get this VA. We'll get this VA and replace it here. Okay, right. So let's do it. Then we'll have a 0 is equal to a 0.05 plus VA is just 0.1 divided by T sine 40 and times cos 40 times T minus this one just becomes what's half of 9.81, half of that. This is a 4.905 T squared. Right, so working on this, we cancel out T like so. Alright, so this, writing this, it becomes a 4.95 T squared. We bring it to the other side and we leave this stuff, which is 0.05 plus 0.1 divided by 0.1 cotangent cotan 40. Right, so therefore we'll have two values of T, positive and negative. Don't have negative time, so 0.05 plus 0.1 cotan. So if it's not there on the calculator, you can just say cos 40 divided by sine 40 divided by 4.905 and square root of that. Then we have a time, which is 0.1857. Okay, this is the time that it takes for the particle for water to move from A to B. So if this, we can calculate this V. So using this equation, we can say, so we know here that T is equal to 0.1857. If we are to plug it in there, then we'll find that our V A minimum, this one is supposed to be minimum, is going to be equal to 0.1 divided by 0.1857 times sine 14. This gives us a 0.8378 meters per second. So this is the first part. So we need to find the other one. Okay, let me just check this again. Cos 14 divided by sine 14 times 0.1 plus 0.05 and divided by 4.905, then square root of that, 1857. Okay, 1857 by sine 14 and 0.1 divided by answer. Alright, there we go. 0.1857 sine 14 0.1 divided by answer. Alright, so this is good enough. We found V minimum. So what we need to do now is to find V max. So I'll say from A to C. Let's look at property, the water, the time it takes for water to reach that farm. Alright, okay, so what do we have? Of course, we are using the same equation. So let's start with horizontal motion. So we have S equal to S naught plus V naught plus half ACT squared, and our S in our case here is 0.035, right? 350. That's 250 plus 100, of course, divided by 1000, 0.35. And then we have S naught, which is equal to 0. And then we have V naught, which is equal to VA. Mind you, here we are dealing with minimum. This is minimum. Okay, this is minimum. This is all minimum. Alright, so VA sine 14. Okay, sine 14. Let me write it like so. This is VAX equal to VA sine 14, and then we have AC, which is equal to 0. Then from this we can have a 0.35 equal to VA sine 14. This we are multiplying it by T, and making VA subject to formula, it just becomes like so. Okay, right, so let's go to vertical motion. We do the same again. Vertical motion, we are using the same equation like so. like so. And then we have s here. S is just going to be equal to 0. Then we have s naught, which is 0.05. Then we have v naught, which is equal to VAY, and this is equal to VA cos 40. Then we have AC equal to minus 9.81, and therefore we'll have a 0 equal to we have a 0 equal to 0.05 plus VA cos 40, okay, minus half by 9.81 t squared. Okay. Then replacing this, we are going to replace this here. Let's get this, we place it there. Okay, we replace this there. Once we do so, then we are going to have the following: 0 is equal to 0.05 plus VA is 0.35 divided by t sine 40, then by cos 40 by t, then minus 4.905, right? 905 t squared. Of course, this part and this part goes. So let's work out now. Here we're going to have the value of t. We can write this as 4.905 t squared equal to 0.05 plus 0.35 cotangent 40. 0.35 times cos 40 divided by sine 40 plus 0.05, then divided by 4.905. Then square root of that, we have t equal to, plus or minus, just interested in the positive, 3086. This time must be longer than the other one, is it? Let's check. It is. Let me check it again. 0.35 cos 40 divided by sine 40 plus 0.05 divided by 4.0905, and square root of that, 3086. Alright, so this is the time. So then using this equation here, you know that time here is equal to 0.3086 as 0.3086. Plugging it there, then we are going to have VA max, which is going to be equal to 0.3086 sine 40, and then 0.35 divided by answer, we have a 1.176 meters per second. So 0.3686 sine 40, and then 0.35 divided by answer, we have 1.76. So we have the maximum and the minimum. This is what they are asking us to find, right? So there we go. So these are the maximum and minimum velocities, speeds. All right, since they are scalar values, speeds that we need. not to allow water to splash on either edges. So I hope this particular video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and I'll see you in my next screencast.